Hello, everyone. So we'll maybe get get started. I know our headline speaker is just finishing off, so we'll maybe have some more attendees trickling in over the next minute or two. But my name is Jason Hawkins. I'm an assistant professor at University of Calgary, and I'll be chairing this session today on transportation data and analytical methods. Our first speaker today is going to be Zamzam Al-Rawahi, who is a PhD candidate at Delft University of Technology in the Netherlands. She is working on developing integrated approaches for effective and inclusive policy by combining traffic and mobility management strategies. And before joining Delft, she completed her bachelor's in civil engineering from Oman and master's in transportation planning from Japan. So whenever you're ready to share your screen, Zamzam, feel free to start.
Thank you very much, Jason, for the introduction. I'll just share my screen. Hello, everyone. Thank you for joining this session. My name is Zamzam, and this research, I'll not do any further introduction. As Jason already mentioned, I'm currently a PhD candidate. And for this research, this was done as a collaboration with Professor Tomio Miwa from Nagoya University in Japan. And in this research, I'll be talking about identifying hypothetical bias in stated preference surveys using a latent class approach. So as you know, surveys are one of the very powerful tools to collect data in transportation. And basically, there are two types of surveys, either stated preference or revealed preference. For the revealed preference, usually the respondents are faced with questions about their current travel behavior. So the collected data will be real data. On the other hand, for stated preference surveys, they're usually used to forecast the demand for a future transportation service, or also sometimes to assess or value the attitude of respondents in the future toward a specific service in the transportation field. And usually because respondents are asked about something that's not existent, so they are faced with a hypothetical situation. And that would cause some hypothetical bias in their answers. And that's because of basically two reasons. It's either content responsive behavior, so they are intentionally answering in a biased way, or sometimes it's also content non-responsive, so they are unconsciously answering in a biased way. In any ways, this will create some biased data in the stated preference surveys. And those are some examples from literature that they argue that respondents usually answer in biased way. They sometimes overstate their economic valuation of a good by 2 to 3 factors. Sometimes they would overstate their willingness to pay by 25 to 50% or more compared to their actual behavior. And sometimes if there is a benefit to be gained from not doing so, they would not reveal their true preferences. So these three types are all content responsive. Sometimes they will just answer carelessly or without reading the question, so that would be content non-responsive. In any way, that those behaviors would create some types of hypothetical biases. So, so far, there is no accepted general theory that explains why really individuals behave in this way and create this type or those types of biases. However, some research have been already done to try to calibrate the data in order to get more accurate data for the estimations of or forecasting the demand. Excuse me. So some of those calibration methods could be ex ante before distributing the survey itself with some methods. And some calibration methods could be done after distributing the survey and once or before start the data analysis. But again, there is no concrete methodology to eliminate those types of biases. And here comes the importance of this research, which is to propose a methodology that could classify respondents into two groups. We named them as responsible and irresponsible respondents. And the aim is to eliminate hypothetical bias, which means once we could study or segment those respondents into a responsible group, you could eliminate them from the data analysis, so we can have more accurate results in the final results. So the data used for this research is a web-based survey conducted in Ho Chi Minh City in Vietnam. And the area was selected because in Ho Chi Minh City, the only available public transportation is public buses for the time being. And in the future, the city is planning for some future public transportation like mass rapid transit, bus rapid transit, monorail, and tramway. So this survey was done to measure the attitude of people towards those new types of public transportation services. The target respondents were commuter respondents, and the data size was 949. The type of data collected were mainly 4 categories: personal information, including socio-demographic characteristics and travel behavior. The psychological data included consciousness for car and bike, bus use, transport situation, and local government activities. And of course, there are the RP and SP data. For the revealed preference data, they're asking about, the questions are asking the respondents about their current public transportation use. And for the SP data, their future public transportation use. On the right-hand side, you can see an overview of the collected data. The females are slightly higher than males. The majority of the respondents were between the age of 23 and 49. And their daily mode, the daily used mode for commuting is mainly motorcycles, which is like approximately 87%. For car, it's 1.9%, and for public buses, it's 4.8%. So this table shows 5 3-level factors that are used for the stated preference questionnaire. The factors are travel time, travel cost, in-vehicle congestion level, and social interaction, as well as travel time by private vehicles. And for each factor, there were 3 levels. So using Taguchi orthogonal arrays, we have concluded 18 hypothetical situations. And for each respondent, there is one case that's randomly shown, so they can answer or estimate or answer their behavior toward that hypothetical situation. So moving to the methodology, so basically the method focuses on testing consumer heterogeneity, and that is by segmenting the respondents into groups. And so then we can study the characteristics of each group. And so how can we classify those respondents into a group? There were a set of indexes we have used. So I'll explain the indexes in the next slides. And then we will categorize those data into 2 groups, as I have mentioned. The first group will be called the responsible respondents, and it's abbreviated as RR. And the second group is the irresponsible respondents, and it's abbreviated as IR. So what we are expecting from this experiment is we are expecting that one group, which is the irresponsible respondent group, would show higher bias. That means we are expecting to see some unreasonable regression estimates than the other group. This shows the methodological framework. So we will start by latent class choice modeling to classify the respondents into 2 groups. So G1 is group 1 for responsible respondents, and G2 is group 2 for irresponsible respondents. Once we classify those 2 groups, we will estimate the models simultaneously for both of them. For the first group, we will use bivariate ordered probit model. And for the second group, we'll use univariate ordered probit model. And in the next slide, I'll show the steps in more details. So let's start with the first part. So to use, this is the utility function used for the latent class modeling. And the classification indexes we have used are basically two types of classification indexes. The first one is the using sociodemographic characteristics of the respondents. And I'm using three indexes here: the gender, that was dummied for males, the household income dummied for low income, and the education level dummied for high income. And this type of index, or this category of three indexes, are used to capture the content responsive bias. And then the other category is using, we have introduced this category to address the content non-responsive bias, which means respondents actually are not reading the questions. They're just answering the questions, so they can just finish with the questionnaire. And the three indexes we have used are likelihood, and it was dummied for lower variables. The long string index, that was dummied for higher variables. And the intra-individual response variability, that was dummied for smaller numbers. And then the respondents will probabilistically be assigned to either. So they will be either assigned to the responsible group or not assigned to the responsible group. The next step would be to estimate the regression analysis, to do the regression analysis for each group. So for the first group, which is the responsible group, we used bivariate ordered probit model, and these are the utilities used. And the reason why we used bivariate ordered probit model is that because we assume that this group is answering the questions responsibly, and so the error terms are correlated between the RB and SP. And then this is the probability used for this group. So the estimation method is RB-SP estimation method. For the other group, these are the utilities used, and we are here assuming that error terms are not correlated, and so this is the probability used to estimate the utilities for the other group, which is the responsible group. So here are the results of, firstly, I'll show the results of the classification of the data. So there are three groups of data were classified based on different indexes. So basically, we have classified those data into three models. You can see the indexes of classification here. The first one is the personal characteristics. As I have mentioned, we have used three indexes. And in all three models, we have introduced those personal characteristics to classify the groups into the responsible and irresponsible groups. For the other content non-responsive indexes used, we have introduced them in three different models. And the reason we did that is because when we introduced the three of them in one model, we found them to be very highly correlated. So we have decided to separate those indexes. So each model will use one index. So the first model will use the personal characteristics as well as the likelihood. The second would use the long string with the personal characteristics, and the third would use the intra-individual response variability with the personal characteristics. This shows clearly how we are classifying or how the variables are dummied in each model. So for the first model, as I've mentioned, we have used the likelihood. So we have dummied the 15% lowest values for the likelihood. For the second model, we have dummied the 12% higher values. And lastly, for the intra-individual response variability, the 6% were dummied. And I put these figures so you can see how see how we have some outliers in those data. And so the outliers are dummied for either lower or higher values depending on the index we're using. And finally, the results for the estimates of the ordered probit model for future public transportation use frequency. Sorry, I think I haven't mentioned this in the beginning. So the estimation of the utility is based on the future use of public transportation. And this result is for the responsible respondents. You can see here, we have found that the travel time, travel cost, and social interaction are found to be, or found to show some reasonable signs, and this is what we anticipated for the responsible group. If we compare it to the results of the ordered probit model in the future public transportation use frequency for the other irresponsible respondents, so this is a typo mistake here. This is the irresponsible respondents. As you can see here, for the travel cost and congestion level, they are showing unreasonable signs, and this is what we anticipated for the irresponsible group. Other variables are not really showing something unreasonable, but they're also not significant. Some other important conclusions from these analyses are that the results of the three models show significant coefficients for the demographic and socioeconomic variables. So when we use the personal characteristics to classify the respondents, they were shown to be significant. And this really aligns with some findings of some research that have shown before that using demographic and socioeconomic characteristics to classify data into responsible and irresponsible groups, or reasonable and unreasonable answers, was also working with some researchers, as for one example is Webster 1989, that he found when he could segment the set of consumers into two groups based on their demographic and socioeconomic characteristics. Regarding the other three indexes we have used to classify the content non-responsive behavior, which is the likelihood, the long string, and intra-individual response variability, in the three models were found to be significant, but with an opposite sign, which is something not what we expected. And one possible reason we could think of is the functional form approximation. And this means when we are analyzing the data using few or no results, or just very few data set, we could have this functional form approximation error. So here comes the future recommendations. We could introduce another index to classify the data, considering the actual commuting frequency and future commuting public transportation use frequency, not only the future use of public transportation, as we have done in this research. And also, we could re-estimate the model using a sample size with a larger group size, as I have mentioned. Because of this error, we have the functional form approximation, because we have used few data for the irresponsible respondents. And I've shown in one of the slides that we have used 15% for the likelihood, 12% for long string, and 6% for intra-individual response variability, which is very few. So we can increase this threshold to either higher or lower, depending on the data, and to see how robust the classifications would be in those choices. And also another suggestion would be to include more variables in the utility function to improve the estimation results. These are some references if you want to refer to some of the citations mentioned in the presentation. And thank you for listening, and feel free to ask me any questions or if you have any suggestions.
Great. So there's a couple questions in the chat box. The first is, what are the actual LL, which I assume are log likelihood? So what are the actual LL and IRV and long string actually representing? What data did you use to calculate those?
Oh, sure. Thank you for your question. These are used for the psychological questions. And so the likelihood is to, I don't think I have, no, I haven't included the pictures. So for those psychological questions, we have firstly, the likelihood is to see how many consecutive answers are the respondent answering. So let's say for the first 7 questions, they're answering highly agree, and for like 7 questions, and then for the next question, they're answering the same thing, and so on. So we have like blocks of answers, so we will find the likelihood of these blocks. For those psychological questions, we will calculate the number of blocks, which are representing the consecutive answers. For long string is also the same, but we are calculating the longest string for each question, for each respondent. So for this respondent, the longest consecutive answers were like 10 questions. He or she is answering the same answer, like totally agree for 10 consecutive questions. So the long string value would be 10 for that one. For inter-individual response variability is to calculate the standard deviation of the consecutive answers of those psychological questions, and this is mainly to test the quality of each response.
Great. So there's one other question in the chat box. I'll maybe let you answer that question in the chat, and we'll move on to our next speaker, who is Vince Bernardin, who is Vice President of Caliper Corporation and has project experience in 29 states and 3 continents. So diverse experience, published in a variety of topics, including passive data expansion, destination and mode choice modeling, forecasting of autonomous vehicles, and complex travel patterns. He received his BA in philosophy from the University of Notre Dame and an MS and PhD in transportation engineering from Northwestern. So whenever you're ready, Vince.
Thank you, Jason. Let me just get the screen sharing going here. Well, thank you. Glad to be with you guys today. I am presenting on some interesting stuff. In some ways, in the larger context, related to Moshe's wonderful introduction this morning. The context here actually is a research project for the Federal Highways Travel Model Improvement Program, the goal of which is to improve travel forecasting using AI and big data. And this is really what I'm presenting today is basically the results from the first stage of this project, which are kind of the literature review and a meta-analysis of that literature. I want to acknowledge my collaborators here at Caliper, as well as our wonderful expert panel, especially Francisco, who's been involved in the work. So the focus of this team at project are kind of on near to midterm improvements. So we're not looking at entire new frameworks for travel forecasting or travel model architectures, but rather kind of on more realistically opportunities to replace component models, within a given architecture, be it activity-based or trip-based or whatnot. And we're focusing on AI DCM models, as they're being called in the literature, which I'll explain in a moment. And in particular, we're focusing for this project on their application to destination choice, because we see it as the largest opportunity for gain, right? So traditional methods, even some relatively simple nested logit models, can do a decent job with things like mode choice, but destination choice, there's a lot of room for improvement. You can see this is just one example, but from a widely cited paper, Nature, the neural network called Deep Gravity, and comparing that to the traditional gravity model and traditional logit destination choice, and then this relatively simple architecture but deep neural network deep gravity, and you can see the impressive improvements in goodness of fit. So again, so in the context here, AIDCM models are basically just combinations of logit and neural network models, right? And there's a number of different ways that you can integrate or combine logit and neural networks. And several have been proposed in literature. We're looking at a couple of them, but we are, I think, particularly focused on TB ResNets, which is just a simple ensemble of a logit model and a deep neural network. And part of what attracts us to this is the interpretability, right? Because the whole framework, can be interpreted as a choice model, right? And so we can look at the plot and examine the utility functions, in some ways, looking at some of the things that Moshe was talking about in terms of monotonicity and so forth, and whether these kinds of constraints that we have based on our expectations about behavior are met. So obviously this is a different approach than what Moshe is proposing, but in some ways getting at at things similarly. And I think this is very exciting. And the reason we're excited about this is you can see here over on the left the pure logit utilities, which are perfectly rational and so forth. You can see here the pure neural network utilities, which are highly irrational. And I don't think we would ever want to do any kind of forecasting or policy analysis with these, right? But the neat thing here is that the data can actually tell us the proper mixture of these, right? And depending on what criteria we use, accuracy, F1 or whatnot, we get an answer that the true model is somewhere here between these two models in the middle. And if you look at the behavior in these models, it's very plausible to me, right? You see this initial, with from paying nothing to paying 50 cents bus fare, I don't like that. But then from paying 50 cents to, a buck 50, $2, really don't care that much, right? But then as we start to get more, 253, but then I start caring again. I start caring a lot, right? And so these are not perfect, and these wouldn't quite meet Moshe's strict constraints, on monotonicity, but they're very close. They're approximately boundedly rational, and I think very believable and defensible. So this is the broader framework, but so the question that we're trying to answer here is we're looking actually, I should go back to, on the neural network side of this ensemble, what is the best architecture, right? So we're looking and we're reviewing the literature on the on neural networks for destination choice. We identified over 350 papers, starting, believe it or not, in 1993 through the present. There really was not a whole lot, though, until beginning in 2016, because in 2015 there was a Kaggle competition where they used TNC data, taxi TNC data, and this just sort of following this, there's an explosion of interest in basically what is destination choice, what we call destination choice in the data science community. Anyway. We identified, 8 branches of the literature using, a number of different criteria, looking at the year of publication, at the literature that they cited primarily, who cited who, and so forth, the type of journal, the application, whether it was to all travel, to commuting, to transit travel specifically, to taxi TNC data, or to social points of interest data, things like looking at restaurant choice with Yelp data or things like that. And whether the problem was formulated is, with constraints or not. This is kind of the history. As I said, there's a little bit early on, mostly in the geography literature. And then, it kind of tapers off until that, after that Kaggle competition, the literature just explodes. something just worth noting in passing is that one of the tricky things here is the formulation and whether these models are, singly or doubly or unconstrained. And this is something that I think is not being thought about, and I want to draw a little attention to, but I'll just say that quickly. So this is the early literature. You can see branch A is where it all starts. Mostly in the GIS geography literature, focuses initially on commuting, and it mainly focuses on very simple, MLPs. The second branch, begins in 2007. It is the very beginning, the first data scientists to look at it, initially looking at taxi TNC stuff, but later they shifted more to a focus on transit trips. These are direct demand, unconstrained models. Initially, they're also looking at MLPs, but later look at other methods. Then this is kind of following the explosion. Paper C1 here is the Kaggle competition winners, and you can see everything that kind of comes following them, and a very influential paper the following year. So you can see branch C, which is data science literature. And so forth. I'm just going to kind of run through these quickly because I'll summarize. If you want, this is in the report for Federal Highway, and I'll summarize these in a couple slides here. Here we have some summaries. This is looking at kind of how new or old the data is. What percentage of the papers are in the data science literature versus transportation and geography and so forth. How much, what percentage are marketing type applications, whether they're generally whether they're direct demand or singly constrained, and how complex they are. You can see there's some distinct differences. And then when we look at kind of methodologically at the actual architectures and methods of the neural networks, you can see even kind of more interesting diversity. Here we have kind of the different dimensions being fully connected networks, convolutional neural networks, recurrent neural networks, graph neural networks, attention mechanisms, embeddings, and generative AI here recently. And you can see how different branches of literature have explored very different architectures and combinations of techniques in terms of using neural networks for this problem. So obviously there's a lot of literature, right? So we did our best to summarize and review as much of it as we could, but we needed an approach to handle kind of all this and wanted a more quantitative method as well. So of course the question is, how do we compare these many papers when they're reporting? They're using different metrics to report their results and compare their results. There are 22 different metrics, not counting all their variants in the literature. Some people using fitness metrics, others using error metrics. Our basic assumption was that the relative improvement in fit or decrease in error are comparable, though they're clearly not identical. Regardless of the fitness or error metric use, right? So, if you say that essentially in the end, regardless of whether you're measuring it with accuracy or recall or root mean square error, if you say your model is 20% better than this other model, regardless of how you're measuring better, we think that could be compared to another claim that this model is 30% better than that one or whatnot, right? So the approach here is to model a latent generic fitness measure, which minimizes the square error between the modeled these modeled ratios, these modeled improvements or whatnot, and the published comparisons, actual published comparisons. This latent fitness metric we defined on the unit interval, like an R squared or whatnot. Our model is just a simple binary logit, for that interval. We had 10 methodological dummy variables, and we just did some simple, least squared errors with a little regularization term. We had in terms of a lot of papers reported multiple fitness or error statistics, so we got to choose in those cases. We preferred normalized metrics, and particularly ones that were normalized on the unit interval. In terms of the data, we had 629 relative comparisons of models published in 81 papers, which used 176 data sets. So a really nice kind of data set of the literature to work with there. Our model exhibits a pretty good fit, so we feel good about our assumption that these comparisons are meaningful, even though they're clearly not perfect. These are the scatter plots of the published versus our synthetic modeled ratios or relative improvements or whatnot. We also did something interesting in terms of testing for authorship bias by attempting to estimate a weight to down, for the least squares error, do weighted least squares error. And interestingly found there was, no evidence for authorship bias, which was slightly surprising to me, but in some ways very encouraging. The results of the analysis, you can see here, from our model and the average scores and so forth. Probably not surprising to folks in general. The generative AI methods really did significantly outperform simpler deep learning methods, deep neural networks. Semi-supervised learning also helped, and to some degree, graph convolutional neural networks also did a little bit better. It's worth noting that there's limited literature so far, and so modest sample sizes for the generative AI. I was encouraged or relieved maybe more that generative adversarial networks were actually the highest performing architecture, and because I'm still scratching my head how large language models do as well as they do with this. But so anyway, in terms of recommendations for what we're doing now, in fact, in this next stage of the project, there are a few things. One which probably is not new to anybody here in more of the academic setting, but in the practice, I think it's really important. It's unfortunately not common enough for people to be thinking about out-of-sample validation and using holdout samples and so forth. So this is something we're emphasizing. Another really key thing, though, an insight from this was thinking about those error metrics and what is the proper error metric. And for destination choice, we were convinced that the proper metric is really a Wasserstein distance, not log likelihood. Right? Log likelihood is obviously, the proper way for measuring true categorical classification problems, in terms of like favorite fruit, right? Where you're comparing apples and oranges, right? But where you're comparing destinations, which, exist in space and are related spatially, log likelihood really isn't the proper measure. And this is my little toy example I like to illustrate. Here in blue is the observed distribution or the observed data. And then we have two models, an orange model and a gray model. And, again, if these are, if A, B, C, D, et cetera, are fruits and, they're just categories, then log likelihood tells us that both orange and gray models are just as wrong. And that's perfectly fine, right? But if these are actually zones that exist in space, right? So that A is on the west side of an urban area and H is on the east side, right? And zone C is between zones B and D and so forth. Then in that case, it's clear that the gray model is significantly better than the orange model, right? Because even though both the orange and gray underpredict how many people are going to H on the east side of the region, the gray model is close. It gets a lot of people to zone G, which is right next door, right? So the Wasserstein distance correctly indicates that the gray model is significantly better, right? Wasserstein distance, has been really important in image recognition and generation in machine learning. It shouldn't, surprise us that this is really important for destination choice as well. So beyond that, then in terms of the architectures that we're testing, again, based on the meta-analysis, we're kind of testing three kind of groups of neural network architectures within that TB-ResNet AI DCM framework. One is a generative adversarial network based kind of on MoveSim and TrajCAN. Another is based on the highest performing non-GAI neural network architecture. And the third is deep gravity, which is sort of our baseline reference for comparison. So that's it. And if we have time for questions, I'm happy to take them.
Great, thanks very much, Vince. I know for myself that I wasn't familiar with Wasserstein distance, so learned something new today that I'll have to look into more.
Yeah, it's it's been a big thing, as I said, with image recognition and generation.
Okay, yeah, because I do a lot of work on destination choice, so that would be I have a current paper on it at least, so that'd be interesting too. Any questions for Vince? Okay, well, if any questions pop up, feel free to put them in the chat box. But otherwise, thanks again, Vince, and we'll move on to the next speaker.
So I'll start. So topic of my presentation today is transferability assessment of housing price within an integrated urban model. This is a collaboration between my supervisor and another PhD student, and I'm just here to present this paper. Okay, so let's get into it. First, I'll give you a brief outline. First, a description of what land use and transportation integrated decisions actually mean. Then I will move on to the Stellar's model, which is the focus of this paper, which is an integrated urban model. And as the focus of this paper is about transferability, I will explain what spatial and temporal transferability actually are, and the basics, the research question, the methodological framework, the data we used, the model results that we estimated, and finally the transferability test results. So first, what are land use and transportation decisions? Our decisions to live, like the locations we choose where to live, actually are dependent on several other things, such as how many vehicles we own, what mode we choose to travel for different trips, how many trips we usually make, what distance we travel. All of them are interdependent in choosing the location in which we want to live. So modeling all of this and using this model to predict urban land use is called the residential relocation. And the housing price is a key component of residential relocation, because obviously when people are buying or renting their houses, the prices are one of the most important things, of course. So in this paper, we'll mainly be focusing on the housing price component of the residential relocation part of an integrated urban model. So first, I will give a brief description of Stellar's. So before going into Stellar's, a brief description of what an integrated urban model actually is. It's a large-scale travel demand forecasting tool. It is able to simulate individuals or households' location and travel choices and their interactions. It is able to predict travel demand, land use patterns, their impacts on environment and the transportation network, etc. And it can be used to simulate or test different integrated land use policies. So in a typical integrated urban model framework, there are three major components: the long-term decision components, medium-term, and short-term decision components. So for Stellar, Stellar stands for Simulator for Transportation, Energy, and Land Use for Regional Systems. It is one of the newer, I would say, newer integrated urban models developed by my research lab at UBC, and it simulates decision making of individual and households over several years. And on the right, you can see the overall framework of scalars. But for this paper, I will be focusing on the long-term decision, particularly the residential modeling part, which has a residential mobility, location search, housing price, and location choice. All of them are separate models. But this paper will discuss the transferability assessment of the housing price component of the residential relocation module. So what are transferability? There are mainly two forms of transferability. One is spatial and temporal. Spatial transferability refers to evaluating if a model developed for one geographical location can be applied to another. And temporal transferability refers to evaluating if a model developed for one time period can be applied to another. So for this study, in testing spatial transferability, we will be focusing on the city of Vancouver and city of Kelowna. And we have developed a model for Vancouver. And for temporal transferability, we will be testing in different time periods in Vancouver. And for spatial transferability, we will test if the model developed for Vancouver can be applied for Kelowna. Why should we test for transferability? Because it reduces the need for extensive local data collection, surveys, and recalibration efforts, thereby saving time and resources. And why did we choose these two cities? Because they are significantly different from each other in population, the size, and also average home prices. So it would be and a good exploration to check if a model is actually applicable in such significantly different contexts. So the research question that we are trying to answer here is how transferable are housing price models, both spatially and temporally, within an integrated urban model. So the scope includes first developing a housing price model for Vancouver in the pre-pandemic time period, which is defined here as January 2016 to February 2020, which will be considered as the base model for this study. And for the temporal test, we will be transferring the base model during pandemic time, defined as March 2020 to September 2022, and post-pandemic time period, which is after September 2022 up until November 2023 at the time of this analysis. And the special test will include transferring the base model of Vancouver to Kelowna for the same time period. So this is the overall methodological framework used in this study. So as I said before, we have developed a model for Vancouver, which is the base model in the pre-pandemic time period. So for testing spatial transferability, we will be using, as this is a simulation model, an integrated urban model, we will be simulating the same model, but with Kelowna data, which is the application context for spatial transferability. And to check if the model is actually transferable or not, we also have developed a local model for the same time period in Kelowna. So we can compare the model estimates and see if the model is actually transferable or not. And for temporal transferability, similarly, we have the base model for Vancouver. And for this, our application context is still Vancouver, but different time periods. So the pre-pandemic model will be applied during pandemic time and post-pandemic period. And for comparison, we also have developed local models using the data from pandemic period and post-pandemic period. And we will be using that to compare against the base model to check if the model is actually transferable or not. So I have just listed some data sources here. I'll not go through all of them, but some of the key data sources include the PC assessment, which is a huge list of all the houses being sold inside British Columbia, the dwelling unit level parcel locations for all several houses. Sales data for comparison have been adjusted to 2023 Canadian dollar values, and supplementary data includes land use data, neighborhood attributes, transportation infrastructure related data. All of them are collected from publicly available data sources. And for variable generation, we have land use data created from by using ArcGIS within a 1 kilometer by 1 kilometer raster, and other neighborhood characteristics and accessibility measures. All of them developed using ArcGIS. So this is just to give a context of how the housing market is different in both these places and in different time periods. So on the left, we see the average yearly housing, average housing price per square feet. So pre-pandemic, during pandemic, and post-pandemic, the trend seems to be similar, but the price ranges are quite different. And on the right here, we see the high housing price per square feet by land use index. So it may seem that the trend is similar, but if you look closely on the left, which is for Vancouver, the slopes are a bit, more steeper on the right for Kelowna compared to Vancouver for all the time periods. So this is just to give a context about how different the housing markets are in both of these places. Okay, so we'll go into the model results. So these are estimated values for spatial transfer test, as in the Vancouver model transfer and the transfer Vancouver model to Kelowna. So these are two different models estimated using data from two different places, but the same methodological framework. And we will be using these estimates to compare to see if the actual Vancouver model is transferable or not. So I will not go into details about the actual values, but these are some of the attributes and the variables that we have used in developing these models. And this is for the temporal transferability test. So all of these models are for Vancouver. One of them, one is for pre-pandemic period, one during pandemic, and one for post-pandemic period. So I will give some brief findings for that we gather from these models, such as for the different cities for Vancouver and Kelowna, winter consistently lowers the prices, but the effect of the winter season varies by city, reflecting the local market dynamics. The single detached homes and large dwellings are valued in both cities, but Kelowna saw a stronger shift toward suburban housing during the pandemic time. High density and short commute time raised prices in Vancouver. In Kelowna, suburban areas gained value, showing diverging preferences generally linked to higher prices in both cities, though Kelowna shows more vulnerability during the pandemic. And for walkability, it adds value in both markets. However, Kelowna showed less consistent effects for transit access and proximity. And for temporal transfer, comparing the estimated values for Vancouver in different time periods, we see that prices consistently drop in winter, similar to before, though the effect is less severe after the pandemic. Strong pandemic-driven demand for larger single detached homes, demand softened slightly post-pandemic, but remained elevated. Pre-pandemic buyers preferred dense, centrally located areas. During the pandemic, suburban living gained some traction, and post-pandemic, in the post-pandemic time, commute time is less influential due to hybrid work. And then preference for mixed-use areas strengthened post-pandemic with less variability than during the pandemic time. And lastly, proximity to transit and retail became less desirable during or post-pandemic. So green spaces and quieter neighborhoods gained some favor. So these are some insights gathered from the different models that were developed. But now it's time for comparison. So when I say comparison, I mean doing some tests regarding transferability. So there are some comparison statistics that we can use to see if a model is actually transferable or not. First is statistical Z-test, which is able to determine whether the parameter estimates of a variable is statistically different between the compared models. All of these comparisons can be applied for both spatial transfer tests and temporal transfer test. The next statistical comparison metric that we can use is transfer row square, which measures which evaluates how well a model transferred one context fits the data observed in another. The equation can be seen here, which uses the log likelihood of the models. And another one is the transfer index. The formula for that is also shown here, which also uses the log likelihood values of the models. And apart from that, we have also used some predictive measures to see to compare between the models, which include root mean square error, RMSE, and mean square prediction error. So now for the transferability test results. So for statistical comparison, Z-test confirms significant differences in parameter estimates for spatial transferability. For example, the Z value was 3.92 for single detached dwelling. So if it's more than 1.96, we assume that yes, it's significantly different. The transfer row square value is 0.4 for Vancouver model versus 0.43 for Kelowna model. So when the Vancouver model was transferred to Kelowna, was directly applied to Kelowna, the transfer row square value was 0.40, but Kelowna model was 0.43. So separately was 0.43. So these values are quite similar, indicating similar model fit. And transfer index was 0.93. So high performance similarity. And for predictive measures, we see the RMSE value when transferred. When the Vancouver model was transferred, RMSE value was 13.7, but using the Kelowna locally developed model, it was 10.1. And for MSPE, it was 0.07 for transport model and 0.04 for the Kelowna model. So the key takeaways here are, despite some parameter differences and slightly lower prediction accuracy, the transfer model performs well and captures Kelowna market's dynamics. But with minor calibration, model transfer is viable across cities within British Columbia. So these were the transferability test results for spatial transferability. Now for temporal transferability, the transfer row square. Again, I'll remind you, we developed a model for the pre-pandemic period, applied it for pandemic and post-pandemic period. So when applying the pre-pandemic period to pandemic time, transfer row square value was 0.49 versus 0.63, which indicates the lower fit. And when applying it to post-pandemic, it was 0.78 versus 0.79, which is almost identical. For the transfer index value, we see when applied to pandemic time, it's 0.77, which indicates moderate adaptability, but in post-pandemic time, it is increased rather significantly, indicating high adaptability. And in terms of prediction accuracy, we see that in pandemic time, the RMC is 34.4 of the transport model versus 20 of the actual locally developed model, or the context-specific model, and MSPU is 0.14 versus 0.05. This is quite different, which actually indicates poor transferability. But compared to pandemic time, if we transfer the model to post-pandemic time, the RMSE value and MSPE value comparisons indicate better transferability. So the key takeaways here are that pre-pandemic model struggles during the pandemic due to behavioral shifts, such as remote work or space demand, but transfers well to the post-pandemic phase where market patterns start to normalize again. So for further exploration, what we did is we developed pre-pandemic model. We applied it to earlier normal years, so before 2016, and we saw prediction accuracy or predictive consistency. In terms of RMSE comparison, we see that it was for transfer model, it's 138.61 versus local model, which is 136.12, so only 1.8% higher. So the key takeaway for this comparison is that model performs consistently under stable pre-pandemic-like conditions, confirming its robustness and reliability in normal market environments. So the overall findings include, for spatial transferability, the Vancouver model performs well when applied to Kelowna, showing a strong overall fit. Some differences in the parameter estimates highlight the need for local calibration, and predictive performance remains acceptable despite the differences in like large differences in between the regions. And in terms of temporal transferability, the pre-pandemic model does not transfer effectively to the pandemic period due to major behavioral shifts. Post-pandemic conditions are more aligned with pre-pandemic patterns, supporting better transferability, and variable effects, especially for land use and accessibility, became more stable post-pandemic. And the last comparison, which is performance in stable conditions, when we applied the base model to earlier normal years, the model shows strong consistency when applied to other contexts. So this confirms that the model is actually reliable under stable market conditions. So these are the overall conclusions. Housing prices are sensitive to socioeconomic disruptions, as shown when transferred to pandemic periods, with notable shifts during and after the pandemic. Special transferability is possible across similar regional markets, but local calibration might be necessary to improve the accuracy. Temporal transferability is limited under disruptive conditions, but improves as market becomes more normalized. Also, model adaptability depends not only on statistical bit, but also on behavioral relevance over time and space. Evaluating transferability strengthens the reliability of integrated urban models for dynamic policy-related environments or policy-related tests. Transferable models support better forecasting of housing market trends and urban growth across various contexts. And lastly, enhancing predictive components of integrated urban models enables more informed and resilient form of urban planning. That's all from me.
Thank you. Unfortunately, we're not able to take kind of live questions, but if there's any questions for Atul, you can post them in the chat box. But I think we'll move on to our next speaker.
Good morning or good afternoon, esteemed colleague. Thank you so much for being here today and giving us a chance to present our work. I apologize for missing the chance to presenting this myself. Most probably my cold is getting a bit worse. I hope this does the job. I am Ahmed Qutim, a PhD student at Utsunomiya University in Japan. I'll be taking you through our effort to develop a comprehensive survey system for understanding travel behavior and MaaS implementation, with some focus on Cairo's new administrative capital. This work is authored by myself and my dear professors Nobuaki Omori and Ahmed Musa. This study is focused on Cairo, and if you have ever been there, Cairo is a very sophisticated city in terms of transportation. You always have the option to go from anywhere to anywhere, likely easy, but you start doing it and doesn't seem really as comfortable or easy as it sounds, specifically if you are relying on public transportation. People, whenever they have the option to choose between car and public transportation, they just blindly go for a car. Greater Cairo region, which constitutes 3 big cities around 3,300 kilometers square. It's massive, 26 million residents and increasing, rapidly. Densities can go up to 75,000 inhabitants per square kilometer, specifically in all the regions and towards city center. Cairo has a very extensive roadway network with more than 36,000 kilometers of paved road. Car ownership is nearly double the national average. The congestion costs Egypt around 15% of its GDP, and average speeds on some corridors can go to as low as 20 kilometers per hour. However, this is, a study by World Bank, relatively old, nothing more structured is available recently, and things possibly could have got a lot better considering the new infrastructure development of roads and bridges being built currently in Egypt. On the other side, Cairo has a very extensive but fragmented and perceived mostly unreliable transportation system. People don't usually use it out of convenience or willingness, but rather, out of obligation. They always go for a car when they have the option. The system suffers from limited information availability. You have buses, you have metro lines on the formal level. We have on the informal side, we have microbuses and tuk-tuks, three-wheelers, if you are well aware of them. If we look at the model spread for Cairo, 26 million trips, 63% done by public transportation, 21% by car. That's almost 5.5 million trips. However, this is a little bit old study, so definitely the figures have surged far way beyond this, and you can imagine how congested the roads can get sometime. Recently, Egypt have been focusing a lot on building the new administrative capital. It's a remote satellite city, basically, lying on the east of Cairo, around 35 kilometers from New Cairo, one of, again, the latest satellite cities developed by the end of 1990s, maybe the beginning of 1990s. It's a massive city. We're speaking about 170,000 firms, under construction to host around 6.5 million residents. Along with its construction starting 2017, there was a lot of focus on enhancing public transportation infrastructure, a set of initiatives for building sustainable projects, enhancing overall mobility of Cairo, and creating corridors to new administrative capital have been under development. We're speaking about an LRT, 2 monorail lines, Metro Line 4, and also a ring road BRT. The ring road is basically one of the biggest and most congested routes in Cairo. All of these create an opportunity, but actually we had to look at how effective this is. And this question we came across through our work at the beginning. We wanted to see if it's really serving the purpose. And in a previous study, we looked at how the new public transportation lines currently being developed enhance travel time and reachability. As you can see towards city center on the left, we can see a good reduction in overall transportation and travel time needed to get to some places, mostly in the range of 10 to 30 minutes. However, when we look at the coverage, only new administrative capital is benefiting and being truly served as reachable or coverage enhanced through the new modes. This led to another question, which is basically the core of these studies. Can this fragmented existing system of public transportation, along with the new set of modern high capacity transportation infrastructure under development, along with a layer of mobility as a service solution, where basically you have information provisioning, model integration, multimodal trip planning, can this combination really, drive sustainable travel behavior with people? For this reason, we developed this dual approach, dual phase design, considers a revealed preference integrated with a stated preference survey to see, simulate the MaaS potential or put people in such hypothetical scenarios where they can choose, allowing us to understand the impact more vividly. On the literature side, you can see, we know all about traditional RP surveys, paper computerized systems evolving over 20 years to GPS or smartphone systems. Some of the challenges, basically, including battery depletion, participation rates, we have seen all of this throughout the studies, as we will show you later. On the other side, for stated preference surveys, a great concept for replicating hypothetical MaaS scenarios to assess factors in decision making. Traditionally it can be done through static tables, however, limited realism and efficiency, or alternatively go in the direction we pursued, which is basically context-aware variance with credible scenarios, enhancing realism and bias. At the beginning of our study, we wanted to use a state-of-the-art smartphone mobile GPS-based system. We used Itinerarium, which is basically developed by Patterson in 2019. We downloaded the repository. It was incomplete. The mobile application had some deprecated packages. The parts of the backend were missing. We completed all of this, dispatched a working version to our initial focus group of 10 participants, mostly family and friends. However, participation was very low. People felt they were continuously tracked, caused them anxiety, they couldn't go through with it. In most cases, even, specifically with new devices, they received notifications that the application was consuming their battery, leading to the device, putting the application to sleep sometimes automatically. So, we thought an alternative solution. We wanted to develop a revealed preference survey system that's more modern than paper-based surveys. However, we still wanted something comprehensive and more convenient for people on the level of data entry. The system includes traditional questions about household travel survey, and household travel composition, including, the people in the household, how many of them are working, what's your employment type, what's your work location, the pay, the income of the household, and whatsoever. Participants also at the end of the first phase, it was split in 2 phases. Participants at the end of the first page, I would say, they input 5 of their usual shopping locations or more. They can do some, input of their shopping locations. Once this is done, they proceed to another screen where they start by inputting their home location, as you will see right now. and then they enter some other location, which is basically, you know, the next point in their travel diary that they choose. We asked them to choose a typical travel day they remember well and to include a couple of trips, not just a single one. People were responsive in this context, and as you can see dynamically, once they add a new destination point on the map, the system considers the previous point as the origin and adds a new point, a destination. They are prompted to enter, you know, to answer questions regarding the trip origin, start time, end time, purpose, modes of travel, and whatsoever. They have the convenience to enter all the relevant data as they wish. Every time they add a point to the map, a system adds a new destination. If they remove it, the destination is removed. As you can see, it's very dynamic and very convenient. The interaction with the map, you know, where you can see the lines, you know, connecting their destination points, make it more engaging for them. We went through a couple of iterations to reach this point. It didn't seem to be very burdensome to the people. They didn't worry about it, and you know, in most cases, participation was 30 minutes maximum to fill the survey. You know, the logical flow followed the TRP BSRC surveys in terms of the questions. We added some, removed some. The architecture and the stack, the front end is basically HTML5, CSS3 as a front end. The presentation layer, we have Node.js for the back end and MySQL database for database. On the context-aware SP survey side, people, you know, initially are prompted about the study briefing. We give them trivia about public transportation in Cairo, show them a map of the full comprehensive system, including new administrative capital, new modes under development, and you know, this illustrates current and the future comprehensiveness and set the mood for the study. The most important part in this is being the concept. You know, this context aware comes from the fact that basically all participants, they have a destination fixed point, which is basically a point in the new administrative capital, as you will see right now. They are free to enter their whichever start location, their home location in most cases. That's what they've done. But as you can see, they always get to the same destination B, which is basically a point in the new administrative capital, specifically in the governmental district where all the ministers are being moved. Once they put their home location and click the show button, as they did, you know, before that point, nothing else in the survey is populated until this step. Once they click on it, the system shows them an overview of the route to the new administrative capital, and then it shows them first part, which is basically real life trip options, comparing transit option and car option in terms of cost, travel, and time. You know, this part actually, as you can see over here, this real life case, it displays an in-frame element inside the page, which calls the view from Open Trip Planner instance. OTP is basically an open source solution for multimodal trip planning. I would show you right now. This is the trip that they have right there, that the user entered actually as an origin to the destination of the new administrative capital. And as you can see here, they have the first leg basically through a bus, and then the other parts through the East Line monorail. This is a typical trip for someone actually living towards the city center and going to the new administrative capital. It's, you know, right now the most remote location in Cairo. Once the real life trip options are presented, participants go through two other phases. First is a set of hypothetical scenarios with 4 cases showing variance of cost and time, you know, in the range of plus or minus 25% to see how they perceive increase or decrease in cost and time. Then they proceed to a set of hybrid scenarios where they, you know, progressively the system adds more cases, starting from the transit and car for the last case, where they have, you know, transit, car, ride hailing, park and ride, ride hailing and transit, and even transit with cycling option. When they present a couple of other hypothetical scenarios after that, basically related to environmental concerns, preferred mode of choice for last mile connectivity, and if they are health motivated or not. Once this is done, we take them through a very important part, which is basically a set of MaaS bundles they have to choose from. There are 7 cases. I guess we are going for it right now. Yes, as you can see, there are a set of 7 bundles, starting from the higher cost, incorporating from the low cost, incorporating only metro and buses, for instance, going to other you know, bundles which include metro, monorail, LRT, BRT buses, and even ride-hailing and ride-sharing services. Across the survey, as you can see, we highlight always their choice and make it relevant. Interestingly, this is work. You know, sometimes mid-survey they go back, they want to, you know, choose something different. The last part of the survey consists of attitudinal questions, asking them on a scale from 1 to 5 about their, for instance, convenience, the importance of convenience, comfort, reliability, availability, and even some questions about their awareness of the infrastructure development, the new administrative capital, moving or living there, and whatsoever. As you can see, this is the part for the OTP. As you can see, the destination is fixed for everyone. The trips start at 7:30 a.m. in the morning on the same day for everyone, and maximum walking distance is set for 1,000 meters. One of the biggest effort that we had to do is basically build the GTFS data. We had to collect a huge amount of scattered data. We had to build data for the whole new infrastructure under development from scratch. For instance, as you can see on the left, this is the Metro Line 4. We start from digitizing the map even to including all the information. We use the GTFS Manager for this, and as you can see, right now, I assume this is one of the most comprehensive GTFS data available about Cairo so far. To give you a quick feedback again, just to recap, sorry, about this, this is what's the design, the structure, the realism factors, the features, and again, the architecture and stack. It comes with a JavaScript front end, the Node.js backend, APIs for calling Google Maps and OTP, and a MySQL database. To go through some preliminary insights, the cohort included 313 participants. We were biased actually towards, choosing younger generations, which are, digitally aware, and they have good literacy about such systems because they are the potential users, and as well people with high car usage. We're speaking about 94% of the participants have at least one vehicle, and 80% of them used the car as their model share. Some other information regarding the commute, the travel time and distance for work and travel diary, and even the cost as well. If you look at this, you see the current model split versus predicted model shift. As you can see before, from the revealed preference survey data, we can see that most participants usually went for car. However, after basically being aware of more other options, specifically availability of information through MaaS, you can see that people started thinking the shift towards alternative options like park and ride hailing and transit specifically. To conclude, this is a dual system for developing cities comprising a household travel survey, basically an RP survey, and a context-aware SP survey focused on MaaS. The insights show baseline patterns and the potential of MaaS to ignite a shift in travel behavior. Limitations and future recommendations. First comes OTP. Have a problem was actually, or it doesn't take into consideration traffic conditions when calculating the travel time. This is a very, very bad disadvantage on their side. Actually, it could be done some other ways, but I mean, it was not relevant or easy in such a case. This is one thing that we really, just consider as a limitation of the study. The fuel price fluctuations. The fuel price changed twice throughout the study. Basically, it would help people make their mind easier shifting towards public transportation. Yet, this is one thing to mention. And again, we would recommend that future research consider MaaS implementations with behavioral monitoring, and even increasing the size of the sample a bit. To be more inclusive and generalized. Just two other publications, work in progress that we have right now, basically focus on the more deeper insights from the hybrid RMB SP surveys and discrete choice modeling, and other effort is being concluded right now regarding the machine learning techniques, again for travel mode choice behavior in our context of the Cairo MaaS study. It incorporated 12 discrete ML algorithms and 16 ensemble models, considering fusion models and weighted average. And we did a comparison of this with traditional DCM techniques. So just like stay tuned, at some point in time, this could be an interesting work to you. That's it. This concludes the presentation. Thank you so much for bearing with me, and I hope this was interesting to you. Thank you so much.
Thank you, Ahmed. Any questions? Well, typically I have questions, but I also have a cold, so I'm not thinking 100%. So I apologize for that. If there are questions for Ahmed, you can post those in the chat box. Our next speaker will be Mohammed Alain, who is a PhD student at the University of Nebraska, supervised by Dr. Wissam Kantar. But this is work that he did under my supervision when I was his advisor at Nebraska. So whenever you're ready, Mohammed, you can share your screen.
Thanks, Dr. Hawkins. Okay. Can you see my screen?
Yep.
Yes.
Yeah. Hello, everybody. Thanks for being here. Today, I'll be presenting our research titled Integrating StreetLight, EPA Smart Location Data, and Road Attributes, a Random Forest Approach to Multimodal Traffic Calibration in Lincoln, Nebraska. So the motivation for our study stems from limitations in traditional and emerging data sources. Conventional traffic counts, which are typically collected by cities, are sparse and confined to major intersections. This means that we lack network-wide data, especially for pedestrians and bicycles. On the other hand, LBS data, like from StreetLight, provides much broader coverage but lacks precision. Additionally, many calibration methods don't incorporate context like land use or road characteristics and mostly rely on linear models. So our main objective is to improve how we calibrate LBS data using traditional traffic counts by bringing in external data sets. We incorporated variables from EPA Smart Location Database, things like population density, land use diversity, employment characteristics, and so on, because they shape travel behavior. We also added detailed attributes from the Nebraska DOT, such as speed limits and number of lanes. These variables now allow us to model traffic more contextually rather than just correlating counts with LBS indicator, location-based services indicator. Our ultimate aim was to improve prediction accuracy for vehicles, pedestrians, and bicycles, especially in cases where LBS data alone underperforms. Such accurate predictions can benefit in applications like planning, safety analysis, which multimodal traffic data becomes readily available. We used 4 main data sets. First, the city of Lincoln provided multimodal traffic counts at 422 intersections from 2014 to 2022. These are our ground truth values and cover vehicles, pedestrians, and bicycles. Second, we used StreetLight data. This is LBS data derived from mobile devices. It provides mode-inferred indicators by road segment and time period. Third, we incorporated the EPA Smart Location Database. This includes over 90 census block group level variables covering land use, population, employment, and network structure. Finally, we added road attributes from the Nebraska DOT, things like lane count, functional classification, medians, and shoulder types. Together, these data sources allowed us to build a comprehensive and enriched modeling framework. The integration process was nuanced. For vehicle volumes, we matched City of Lincoln turning movement counts to StreetLight segments by considering traffic flows on each intersection leg, as indicated by the figure here. For pedestrians and cyclists, we aggregated volumes on the intersection level. We also ensured that temporal alignment between data. We also ensured that there is a temporal alignment between the data sets. StreetLight defines day parts like AM peak and PM peak, so we aggregated the City of Lincoln's 15-minute counts to exactly match these day parts. Next, we integrated the contextual data. EPA Smart Location data variables are at the census block group level. So we performed spatial joins to attach them to the StreetLight segments. We allowed many to one joins, meaning that a segment could have inherent features from multiple block groups. So we preserved as much feature variation as possible. Similarly, we mapped road attributes like lane count and speed limits to the same segments using GIS joins with buffering used to ensure proper spatial alignment. This is an illustration of the calibration process. So we started with basic statistical models as a baseline. Linear regression helped us explore variable relationships, but it was a poor fit for count data. So we moved to a Poisson regression, which is commonly used for counts, but it couldn't handle the overdispersion we found. So this led us to negative binomial regression, which is a more appropriate fit for overdispersed count data. To manage the complexity of over 100 variables in our data set, we used elastic net regularization. After establishing our statistical baselines, we moved to random forests. Random forest models are ensembles of decision trees. They're excellent at capturing nonlinear relationships and handling noisy, high-dimensional data. A big advantage also is that random forests don't require us to manually select the variables or regularize the model. It naturally reduces overfitting and handles multicollinearity. So we also get feature importance scores, and that coupled with SHA plots, it can help interpret the models, so it's not a black box anymore. We found that random forests offered much better predictive accuracy than negative binomial models, and that's why we will be focusing on the random forest results. Now, moving on to the results, for the vehicle model, we achieved an R-squared value of 0.993 on the training set and 0.947 on the test set, which was excellent. StreetLight volumes was the most important feature by far, with an importance score of 0.77. This shows that LBS data is quite reliable for motor vehicles. Other important features include functional class and speed limit, which are indicators of road capacity and design. These results validate what we expected. Vehicle travel is easier to detect and model accurately using LBS data, especially on high volume roads. Moving on to the pedestrian model, the pedestrian model also performed very well at 0.989 for the testing set. And here, StreetLight volumes had slightly lower importance score of 0.668, but still dominated. The number of lanes had a strong effect, with narrow roads generally areas with fewer vehicles. Tend to have more walking, reducing the pedestrian volumes. Also, the percentage of zero-car households played a key role, which aligns with common sense in the literature. Other contextual variables like population and employment density also contributed in this model. Interestingly, the bike model outperformed expectations with an R-squared of 0.998. That's on the training set and 0.994 on the test set, despite bikes being the most challenging to model. The top feature was still StreetLight volume, but with a lower importance score of 0.363, suggesting that the LBS signal is weaker for bicycles. Instead, contextual factors like lane count and road network density played a much larger role in this case. This, more than any other model, highlights the value of including EPA smart location data and road data in the bike volume models. Are counts random or biased? An important question we address is whether the ground truth counts from the city of Lincoln are representative. The short answer is no. Most counts are from busy, high-volume intersections. Statistical tests confirmed that significant differences between training data, that's the count locations, and the rest of the network exist. This introduces selection bias, meaning our models are likely more accurate on well-traveled roads than on low-volume residential streets. That said, this limitation is common in transportation research, and high-volume facilities are often prioritized for planning and study and safety studies. In summary, all three models outperformed expectations, especially the pedestrian bike models. Interestingly, we added contextual data. When we added contextual data, The predictive accuracy was boosted. EPA smart location data and road features compensated for weak LBS signals in the non-motorized modes. This reinforces the idea that integrating multiple data sources can dramatically improve model reliability. There are several important implications of the study. First, this approach enhances crash exposure metrics by allowing us to estimate multimodal volumes even where no counts exist. Second, it supports safety and equity analyses by revealing patterns in pedestrian bike activity. Because we use publicly available datasets like EPA, smart location data, and NDOT shape files, the methodology is scalable and replicable. For future directions, we recommend focusing on improving calibration for low volume streets and testing the use of finer time intervals. We also want to acknowledge 4 limitations. We first, aggregating 15-minute counts to StreetLight day parts may obscure short-term fluctuations in volumes. As mentioned, if it hasn't been mentioned before, StreetLight splits the day into 5 different periods, and they range from 4 to 6 hours each. So when you aggregate 15-minute counts to a 4-hour-long day part, that could obscure some interesting patterns. The second, and as mentioned earlier, our sample is biased towards high volume roads, which limits generalizability. Third, even though random forests handle complexity well, overfitting is still a concern. There's also the fact that they're not as interpretable as generalized linear models. Well, thank you so much for your time. I'll leave this up for a moment in case you want to scan the QR code and access the full paper.
Thanks, excuse me. Thanks, Mohammed. There were a couple of questions in the chat that I gave a bit of a response, but maybe you have some different thoughts than me. Have you taken a look at or compared StreetLight with INRIX data or Replica or other data in terms of their accuracy?
No.
Okay. Yeah, I know we didn't look at it in detail. Another question was the EPA data. You can get walk scores at the tract or block group levels. Have you seen anything with walk scores across the country at finer levels?
At finer levels than census block group?
Yeah,
no.
so like I guess for an address or for a block.
No, I think block group was just as fine as the resolution of contextual data could go.
Yeah, I think so. But I responded. I think Shusan Joe at ASU has been doing some work on kind of disaggregate network accessibility measures, and he may be able to use what he's doing to do something very disaggregate. But I'm not sure if he could do it to that level of disaggregation. Those would be very interesting. Any other questions? Okay, well, thanks again, Mohammed. Our final speaker today is going to be Ruohan Lee, who is a PhD student at Villanova University and a research assistant in the Nova Mobility Lab, advised by Chengfeng Xiang. Her work centers on understanding, reconstructing, and explaining human mobility through trajectory and bridges data-driven modeling and theoretical thinking in human mobility analysis. So whenever you're ready, you can share your screen.
Thank you, Dr. Hawkins. Hi, everyone. Good afternoon. It's my pleasure to be here. I'm Ruohan Lee, a PhD student from Villanova Human Mobility Data Lab. Today, I'll present our newest work on map matching, the Sup-HMM model, a Bayesian-optimized map matching method designed for the noise and low sampling location-based service data. We also can call it the LBS data. Here's a quick outline. I'll first explain what is map matching and why it's challenging for the location-based service data. Then I will introduce our Sup-HMM model, how we integrate the Bayesian optimization and Markov chain Monte Carlo, followed by some experience and results. First, what is map matching? Map matching is actually an important and foundation process before we use LBS data. As we know, the LBS data is not only give us the raw points, and we can use it from the macro level analyzing, but when we want to it for a micro level analyzing, there should be some extra processing. That's made time consuming, but with the map matching, we can pre-process the raw data, map these raw points to the digital raw networks. So we can analyzing the LBS data from a fine-grained level, such as a raw network, and also can combine with the POI. And that's why make analyzing much more easier. The most widely used for the map matching results is navigation. We may use it every day, like the Google Map, also the rider sharing and the delivery services, and also the public transportation systems. In the traffic and transportation area, we use map matching results for the traffic flow analyzing, road optimization, safety analyzing. And most important is behavior analyzing, like the travel behavior, travel pattern, and the POI visits. Right, figure 2 shows a sample of traffic analyzing using the map matching results before and during the COVID-19. We can see how the traffic activity changed on the road networks. In our case, we apply the map matching to turn the raw messy LBS data into structured usable mobility data, while also present user privacy. As shown in the figure 3, we can reconstruct the complete transit trips on the road networks and identify which station the user actually used. The output is clear and interpretable. It's ready for further analyzing, like the mode detection, travel behavior, and network performance. But as we know, the LBS data is collected from the different devices, such as the smartphone, vehicles, and even Wi-Fi, satellite, and so on. So the trajectory in it may have different sampling rate and points oscillations. The most important, there is no speed and direction information in the LBS data. However, most map matching model target only the vehicle GPS data, which do have the real speed and directions. This helps the model achieve better performance. So this makes the map matching in the LBS data much more difficult than GPS data. As for the algorithm for the map matching, before the probability-based method, the most popular ways is using geometric and the topologic method. This method are very simple and less time-consuming, but very easy, sensitive to noise and less accurate. After this, the probability-based method, like the hidden Markov model, becomes the most popular ways even now. Recently, a lot of researchers want to apply the deep learning or reinforcement learning method to different areas. That also includes the map matching and also the hybrid algorithm method. But why we choose the hidden Markov model as our basic framework? As I mentioned before, we use this model for realistic large human mobility data generations. In this case, the most important, we should consider the different scenarios and also the time consumption. We had used a geometric method in Washington, D.C. data generation last year, but the results were not confident. If we apply the deep learning-based model, we may need to label the data set. That is very difficult. And using the time And we're using the time to train a model which is no transferability to different city or scenarios. So in this case, with the advantages and applications of the hidden Markov model, at least here, we choose hidden Markov model as our map matching basic framework. Okay, move on the map matching framework. Our map matching method divided into parts. Here's our pipeline. We use an HMM based and enhanced it with 3 custom conditions and 2-stage hyperparameter tuning approach using the Markov chain, Monte Carlo, and the Bayesian optimizations. In our Sup-HMM model, observations probability is based on how close GPS points are to the nearby road segments. We use a kitty tree to quick find the candidate's link within 30 meters of each GPS point. When we assign the probabilities using a distance-based functions closer to the candidates and most likely. Now come to the key part, the transition probabilities. We enhanced it with 3 additional conditions, which is why we called it Sup-HMM. As a core, we use a distance-based measure to estimate how likely a GPS point move from the one road segment to the next point. The first condition looks movement trend. We compare the angle between the GPS point with the angle between the candidate road segments, basically checking if the direction of the travel matches the road geometry. The second condition is the detour penalty. We compare the shortest path distance between the 2 GPS points to their straight line distance. If the road is much longer than expected, we penalize it, since it's a reasonable path should start close to the straight line distance. And the third condition is check the speed consistency. We compare the average speed between the 2 GPS points with the speed limits and the candidate road. If the speed doesn't make sense, we reduce the probabilities. So together, these 3 conditions, movement trade, detour penalty, and the speed check, helps us improve the map matching accuracy. Another key part of our method is how we fine-tune the parameters using Markov chain, Monte Carlo, and the Bayesian optimization. Instead of manually setting them, we let the MCMC explore the parameter space first. That's shown on the left side of the figure. The Bayesian optimization kicks in to find the best configurations more efficiently, as you can see on the right. This setup makes the model perform better and adopt different regions and data types. Here we list the 6 hyperparameters we select based on the characteristic of the both map matching and the LBS data. This includes the parameters related to observation error, search radius, transition scale, and as well as the threshold for detour, direction consistency, and speed. All this play a very important role in the shaping the final map matching results. All right, now let's move on to our experience and results. We test our model on 3 datasets. The main one is LBS data from Washington DC area using the road network from OpenStreetMap. This LBS data is very sparse and the noise, which ideally for the stress testing our method. You can see from the second column in the table 2 that our LBS data, the mean sampling rate is just 0.09, and the variance is extremely high compared to the another GPS data. This makes it much more challenging than the 2 GPS dataset from Seattle and Hof, which have a much more clear and denser signals. So the figure 6 on the right hand provides evidence again for the LBS dataset, each trajectories within a different sampling rate. For the evaluation metrics, we use standard metrics like accuracy, precision, recall, and F1 score. We also measure the map match errors with quantified path level differences. Here are the core results on our LBS data, and they really show the advantage of the Sup-HMM model. First, on the left, figure 8 compares the map matching error across the different model. You can see that Sup-HMM model achieved an error just in 0.176. In contrast, the classic HMM model reached as high as 0.78, and even the improved HMM model with a non-emitting state still have error of 0.58. On the right, the figure 9 gives a more comprehensive view. It shows accuracy, precision, recall, and F1 score. Sup-HMM clearly across nearly all metrics and the score above 0.9 in every category. Here we show a visualization of the match trajectory from LBS data. We compare the ground truth with the result from the HMM model with a non-emission state, which is our benchmark, and our Sup-HMM model. We can see that non-emission state model, which is in blue trajectories, takes some round detour in middle sections, especially in area with a non-highway and ramps. Once it's deviated, it struggles to return back to the correct path. So in contrast, our Sup-HMM model results, which is in red trajectories, maintain a stable and accurate path throughout, staying much closer to the ground truth. The ground truth is in the green color. This figure compares our Sup-HMM model with a benchmark model across each individual LBS trajectories. The x-axis shows the trajectories sorted by sampling rate from the high to low. For each one, we plot the map matching error from both models. What we observe is that Sup-HMM model performs much better on low sampling rate trajectories where traditional model usually struggle. And it's also interesting that in high sampling rates, the benchmark model still suffer due to the noise and the oscillations in the dataset. But Sup-HMM model handle this better because the MCMC and BO, the Bayesian optimization helps the fine-tuning the hyperparameters to reduce this effect. Finally, we test our model on 2 additional datasets that is not LBS data. They are standard GPS dataset from Hof and Seattle. Even though the model was trained using only the LBS data from DC, we apply it directly to this GPS data without any retuning. Sup-HMM model still achieve a strong performance, often even better than on the LBS data. This confirms that our approach is not only robust, but also highly transferable. So to sum up, first, Sup-HMM fine-tune itself automatically using the MCMC and the Bayesian optimization, so we don't need to manually adjust parameters. Second is it can handle common challenges in LBS data like detour and unrealistic speed by using 3 smart conditions in the transition probabilities. And finally, the model generalizes well and perform consistently across different regions and datasets. This makes it a robust solution for real-world noise mobility data. And finally, we can use the results to build the path like the figure on the right hand. Thank you for your time, and here are a few visualizations of our results. If you are interested in our research, you can scan the QR code or see more results, and feel free to reach out if you have interest in our details. Thank you.
Great, thank you. So we do have one question in the chat, and if there's other questions for any of the speakers, we do have some time at the end of this session now. So the question is, when comparing the speed of 2 links, is the speed limit in OSM dataset used? The OSM speed limit can be inaccurate sometimes. Is it a possible issue? So I'll start with that because there's 2 questions. So comments on speed limit data from OSM data.
Oh, thank you for the questions. Yes, actually, the OSM is not very accurate. Sometimes the links may missing some speed. So we use the average link speed. And for the more accuracy, we actually use a TMC to map the TMC speed to the network. That is our product to validate it. So in here, we use OpenStreetMap speed. That is open source data. So just in this case.
Great. So then the second question is, how do you deal with roads which are overlapping in 2 dimensions, but they're at different elevations? So overpasses and those sorts of things.
Sorry, can you?
How do you in your work, how do you deal with roads that with interchanges where you have roads at 2 different elevations, so they overlap in 2
yeah,
dimensions,
gotcha.
but they're at different elevations.
Yeah, that's a very important. Actually, sometimes the overlapping may have different types of road links, but indeed, our algorithm cannot handle all these problems. So.
Any other questions? Oh. Well, I think Kay has posted the links for the next set of sessions. We have 5 minutes of breathing room, which I appreciate. So I'll see everyone in 5 minutes. Thanks again for joining the session.